Okay, the goals for this talk are to explain the palladium, deuterium, and nickel hydrogen fusion reactions with some mathematical support. I hope to show this using standard theories based on well-known effects. And then from the model, the parameters in the model, one can determine the thresholds for the reactions and how that's dependent on various parameters like the concentration of deuterium or so on, the diffusion parameters, optical phonon mode occupancies, and the phonon coherence time. And at the end of this, that information will suggest ways to increase the reaction rate, ways to lower the threshold, ways to control the reaction, and better measurement techniques in hope of feeding that back into the R&D process. And then, of course, it'll provide a basis to experimentally verify if the theory actually holds any water. So I'm going to propose some things in this talk which will be a little controversial. And I wanted to quote Alice in Wonderland a little bit, where Alice says, "It's no use in trying," she said, "I can't believe impossible things." And the Queen says, "I dare say you haven't practiced very much. When I was younger, I always did it for half an hour every day. Why, sometimes I believe as many as 6 impossible things before breakfast." Well, in this talk, I'm going to ask you to maybe suspend some judgment, but I'm going to treat deuterium, atomic deuterium, as waves, not hard marble spheres with Coulomb barrier. I'm going to employ something well known in other fields, which is multiple virtual state transitions, which will absorb the phonon, the reaction energy into phonons. I'm going to use a simple interaction integral with that applies to the delocalized deuterium. The deuterium's in a waveform with a Debye wavelength of about a half an angstrom. Using those things, I'm going to explain how these effects occur and yet don't have an apparent impossible barrier, but yet prohibit other reactions such as reaction to tritium or reaction to helium-3, which you might expect if you didn't have a Coulomb barrier issue. So first, one of my first exposures to this issue was listening to the palladium-deuterium experiments. And one of the most striking things about those experiments is they don't release hot particles. As everybody knows, that's a key indicia, allegedly, of nuclear reactions. So why don't they? This experiment doesn't, and so that must have a unique and important explanation. The fact that the heat from the reaction is released without energetic particles pretty much, I would say, very convincingly implies that the conversion of heat is to phonons either directly, straight to phonons, or indirectly through some process. But if it is indirect, whatever that mechanism should be visible, because there's an awful lot of energy, and there'd have to be some intermediate particle that would cause that, and that would be visible. So I'm going to talk about direct conversion and how that could occur, which involves creating about 5 times 10 to the 10th phonons in a process that isn't that commonly understood. So multiphonon relaxation does occur in other fields and is well known, such as relaxation in phosphors, where energy is transferred from one level to another with no optical transition through phonons that have an energy gap that's much greater than the phonon energy present in the crystal. So for example, in laser crystals where this was studied, it might take 6 phonons for a non-radiative transition between two levels. So the reaction is simply described as that deuterons of interest are in waves, meaning they're not thought of as little marbles between lattices. They're just an extension of the quantum mechanical process. And just as an electron is described in the lattice in elementary quantum physics as a wave phenomena. Deuterons are particles in some environments, but can be viewed as waves. And if you calculate the wavelength of a deuteron, it should be about half an angstrom. In that same region, the electron concentration, that in this case, is about 50 times the proton concentration. So the charge environment will completely overwhelm any charge process that would be associated with the deuteron. So the screening you might otherwise expect is minimized because the deuteron has effectively a large size, and the screening effect is compensated for. So the two deuterons together will combine and form helium and about 5 times 10 to the 10th phonons. The reaction rate for this reaction is predicted from higher order perturbation theory, which I'm going to go through in a few minutes. The deuterons in the and a very simple mechanism. This is not a mechanism of hyperfine coupling between some nuclear particles. It's simply a result of compression, a longitudinal compression of the cell, the unit cell in the crystal. That, and I'll go into this in a minute, that compression changes the effective interaction energy of the deuterons a little bit. But since there's 10 to the 5th or 10 to the 10th interactions, there are multiple paths in this multi-phonon path that allows a very substantial reaction rate. So the typical math for any reaction involving a closed system says that you have an initial state or an input state and some interaction, let's say an electric field between particles or phonons or something. It leads to an output state, and the energy in the total system is conserved. The reaction rate for that to occur is described by this famous Fermi's golden rule up there, which says that the reaction rate is 2 pi over h bar times the interaction integral, which is described in green below, and that energy has to be conserved, which is indicated by the delta function there. So the interaction integral, all that is a integration of the final wave state shape times the interaction energy times the initial wave or operator times the initial. So it has the units of energy, and it's a result of spatial overlap of two wave functions, the input wave function and the output wave function. Now, often there are multi-state interactions or interactions of multiple particles, and those can be described by the equations below. All this stuff was developed in the 1930s and is not controversial. Now, in multiple levels with multiple paths, you can have perhaps a reaction with two states, like two successive interactions. That would be described by this rate equation, which is distinguished by two interaction integrals from the first state to the second state, and then, or zero state to the first state, and the first state to the second state, divided by the energy difference between the state, all this squared. And then if there's two interactions, you have a similar integral, and you can see a trend here. And if you go to multiple interactions and multiple parallel paths, which will be our case, you'll see this overall reaction rate. Okay, so it's a product of a whole lot of interaction integrals. And those numbers are very small, like 10 to the minus 15th. And if we're going to talk about 10 to the 10th of those numbers, that product will be an extremely small number. It's somewhat compensated by the number of paths that are taken, and there are this many paths potentially, 10 to the 22, let's say, atoms in a crystal, to the 5 times 10 to the 10th path. So that's, in case anybody from Google here, is much larger than a Googleplex, which is 10 followed by 100 zeros. This is 10 followed by 10,000. Okay, so you can follow that logic through and use the following as wave functions. The input wave function is a 2 deuterium spatial wave functions times a phonon state, which is indicated here by the occupation of the various K modes. And the output wave function is a helium wave function, a spatial wave function, times another phonon state. And I should mention it really will normally have one added to the, or at least the ones with non-zero integrals will have an additional phonon in one of the states. Okay, so you calculate this overlap integral. Now what's different in this case is the direct integral is not something we're interested. We calculated an energy for the overlap region of the phone. Well, let me just go on for a second. The actual interaction energy is the potential from the overlapping deuterons, and I'll get to this in more detail in a second, which is modulated by the phonon changing the size of the cell. So changing the size of the cell slightly changes a low energy a little bit. So you end up with some equations based on all the previous for two situations. One where the this integral here has a bunch of sums inside an absolute value. So you're taking the absolute value of a huge number of products as distinguished from the product of a whole set of absolute values, which would be easier to deal with. So if we assume, and we're going to, that all these interaction integrals are the same for simplicity, except for their phase. If they're all in phase, they'll add up to one large number. If they're out of phase, they'll add up to a number that's smaller by the square root of the number of steps. So you end up with two possible formulas for reaction rate, one with a coherent situation, distinguished by this 2 up here, and one with an incoherent situation where there's less energy. Now, I'm going to show you later that I believe that a significant fraction of these interactions are coherent, but not all of them. So the way to compute this is a way to compute this is to take a fraction of the total number of levels in the solid, not all of them, and use the coherent formula. Okay, so if you do all this stuff, calculating the interaction overlap, imagine a 24 MeV, two deuterons near each, on top of each other, that has a minus 24 MeV energy. Now imagine smearing that over a half an angstrom volume. That energy is going to be a lot lower when you do that average over that volume. Now imagine changing that volume slightly, and this is what a phonon, one phonon or n phonons will change the x ordinate of that cell by. So this is the reduced mass of the in this case hydrogen palladium atom, which determines the vibration mode, the number of cells in the crystal, and the frequency. And I'm not going to go into a whole lot more detail here. So you get a final rate equation, which is this. Okay, for this 5 times 10 to the 10th number of levels. You can plug this into your computer, but you have to convert all these numbers, which are very large, and factorials of even very large numbers. So you convert the factorials to a Stirling formula, take the log, set that all equal to 0, and then meaning reaction rate of 1 per second in this case, and look for sensitivity. Now, so the one question that's going to come up is what number to use for some of the parameters, particularly the amount of deuterium in interstitial sites. And I'm just going to briefly say that one paper suggests that 3% of doping it appears should be to T sites at 300 degrees C, which I'm not going to go into a lot of detail with that. So if you plot those trade-offs on the plot, and you can trade off the fraction of the modes that are coherent is one variable, the number of atoms in the cell, or the log of that, and the number of phonons per mode, you can see some planes. And the third parameter in the various planes are what fraction of deuterons per cell are there, excess deuterons. I'm not talking about the deuterons on the normal palladium deuteride sites. And what you can see is you can get a reaction with cells as small as 10 to the 5th crystals as small as 10 to the 5th atoms. But it can vary depending on a lot of things. Okay. So the problem with this analysis is that it uses an average phonon state occupation, which isn't going to be the case in a real reaction because you'll be building up phonons as you go along. And another thing that doesn't show up is the phonons that are generated are going to gravitate to the high density of state modes in these crystals. That will affect the reaction rate, but it doesn't show up very well in that equation. So we need a better equation. Okay, so now why, if this all happens with helium, or with product of helium product, why don't we see these reactions, which are the normal reactions? And my argument is, well, and this is described by Fermi in the 1930s, in a normal beta decay, you have your beta atoms or whatever, nuclei. And the interaction integral is the product of the wave functions that are coming out and the wave function going in. So that's the interaction integral. Well, when all the wavelengths of these output particles are about the same size as the nucleus, so you'll get an integral that's non-zero. If you go to an interaction size that's much larger, like half an angstrom, you're going to have the same wavelengths of the output products as determined by energy conservation, but the area you're integrating over is much larger, so all these things are going to have an integral which is very close to zero. This is 10 to the 5th radius bigger than this, so when you compute the integral of all these wave functions out of phase, it's not likely to have a very large overlap integral. Okay, so now I want to talk about eigenmodes and phonons because they're an essential part of this discussion. So you can develop a model for eigenmodes and frequencies by using a mass and spring representation of the palladium hydride system, and then you can use that to compute densities of states. In other words, how many phonons there are per omega, or how many modes there are per frequency. You can look at the modes, how those interact with the unit cell, and you can do things like predicted decay rates of optical phonons to acoustic phonons, which will be important. So without going into any detail, you write equations for forces between all these atoms. In this case, it was 12 equations for palladium to palladium and 4 equations for palladium to deuterium. Put that in a secular matrix and solve for the normal modes and the frequencies. What I'm going to tell you now is a summary of what you're going to see in the next few slides. First thing I'll show you is that you can get some very narrow optical phonon line widths, and this is primarily related to the huge difference in mass between palladium and deuterium, or nickel and hydrogen. That'll be even more narrow near the L point of a crystal, which is the 111 direction in a crystal, in a let's call it a face-centered crystal, cubic crystal. Well, it's actually a salt crystal, but if the lattice, this is going to imply that you can get coherence effects, and in fact, you should see coherent phonon modes as a result of these reactions. You also see that maybe nickel deuterium will have fast phonon decay modes, which may inhibit some of these reactions. Also, if the lattice is imperfect, you'll see broadening of the line widths that would come out of this model, which will, in effect, will change the reaction rates, and I'll explain that in a minute. Finally, maybe not anticipated effect is the density of states in long wires will be different in certain directions, and you'll want a high density of state in the direction you're trying to have this reaction occur. So you may imply that long wires in certain directions will have lower thresholds or higher reaction rates. Okay, so using that secular matrix, you can build a model, which I did. And this is a model, and you can input the directions of the phonon vector, the mode. There's 6 modes because there's 6 degrees of freedom in this problem. And you can vary the spring ratios between the palladium, 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 deuterium, and deuterium, deuterium. I set 1, palladium, palladium, to be unity. And you can change the phase. So if I had this live, I could show you phase motion through here. So this is a depiction of palladium, 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 and hydrogen, not at their normal size, but which would obscure the whole picture. They'd all be filling this thing. But the point is, the one mode, these hydrogens move this way, and if there is any interstitial hydrogen in here, it'll be compressed. The longitudinal modes compress the cell. The transverse modes do not compress the cell, and therefore don't, in this theory, have much of a reaction. So here's a computation of the typical density of state computation for hydrogen, or deuterium and palladium. And what you see here is the longitudinal acoustic mode and 2 other acoustic modes, two other transverse modes. You see the longitudinal optical mode and some other transverse optical modes. And one thing I want you to note is how sharp that line is. Now, sharp as it is, if you sample only a part of the K-space spectrum, which I'll show you why that's important, those lines all sharpen up. In other words, if I took, I think, 60,000 sample points up here, and that led to this spectrum. Here I took the sample points at the same density, but only the ones close to the L point in the spectrum. And you see these lines sharpen up. Even the acoustic mode sharpen up quite a bit, but these lines sharpen up a lot. This is going to lead to a coherence effect, which is going to be important for the rate calculations. So I did not put in here in the model the exact elastic components because I didn't know them for palladium, but you can pretty well guess what they are. This is a slide showing the ratios of the palladium spring constant to the palladium deuteron spring constant and this variable and the deuterium constant. So if you plot those and look for sensitivities, you can see, for example, separation between the acoustic and optical modes changes and the sharpness of the lines change, okay? So one thing that's going to be important is knowing the lifetime of the longitudinal optical phonon. And a longitudinal optical phonon will decay to longitudinal acoustic phonons, but it has to conserve energy and has to conserve crystal momentum. So that places a constraint on the reaction. You can do a computation, which I won't go into now, and see the sensitivity of the decay rate in these various compounds to 1 minute? Okay. And you basically can see that palladium, hydrogen, and nickel, deuterium, palladium, deuterium, palladium, and nickel, hydrogen have large potential regions where they basically have low phonon decay rates. Okay, moving on. Okay, now I'm going to talk about phonon transitions, and I'm just going to give you an example. Phonons have to go from one K state. If this is 4 phonon modes, 0, 2, 1, 1, they can only increase in modes into another state by, for example, increasing this phonon 1 and leaving the other ones the same. You can make a toy model of this, and you can see how phonons would progressively grow. And what I'm showing here is going from initial state. Oh, I see. Okay. Going from initial state, I don't dare point. Going from initial state with the black boxes on top there. On the left, you can see the axes are this number of phonon, or the probability of phonon is in a state, and then going down the occupation of the state. So what happens is, as this process goes along, you get more and more phonons in the 1-1-1 state. You're getting rapid growth of a preferential direction, which will lead to coherence. So I showed you a big computation Now I'm saying, okay, how can we determine the threshold? Well, you can determine the threshold if you can get from one state to the next state and generate one additional phonon. So the question is, how do you do that? And without going into a lot of detail, there's when you add a phonon, I have to use this. Okay. When you add a phonon, if the phonon, well, there are coherent transactions, and if they're coherent, you get much more amplification of the rate. So the question is, how many phonons are in a essentially, I'll say a coherent mode? That is a function of the previous history of the system. But the bottom line here is there's an equation which will now describe the threshold for future ever-increasing phonon reactions. Oops, that wasn't supposed to be there. So the conclusions from the model, okay, there is a system that can, relaxation of the system that can occur because of the huge number of channels, and I told you it's much larger than the Googleplex. The mechanism of modulating the cell size is at least one way to provide a matrix element which appears reasonable despite its tiny values and does actually come up with something that looks reasonable. It's also possible there's other matrix elements that have phonon, that are related to phonons, which would have the same math. Phonon lifetimes and coherence related to line widths and state occupation, along with crystal size, determines the threshold, and along with the doping. So these are things people aren't paying much attention to right now. The releases of energy is accompanied by increased coherence, and I would say you basically have a acoustic laser here. And once you know all this stuff, you can figure out what to do better. I think I'll just skip this for now. So threshold is, as I showed you, that threshold equation is can be attained many ways, basically satisfying the conditions equation. But artificially, you can do things like change the temperature. You can provide laser or other stimulation to change the phonon count, basically outside of the nuclear process. So you basically inject phonons. You can do things like change the orientation of the crystal and make tall and thin. And you can have crystals with narrow line width and long phonon lifetimes, which I can't go into enough detail right now, but those will lower the threshold. Okay, same thing with nickel hydride, and I'm surprised that people haven't actually measured the output of these reactions to find out if indeed we're getting deuterium out of them, which I would hope they would based on this model. But there are big similarities between the two systems, but there are quite a lot of numerical differences, so naturally they don't behave just the same. Okay, so some things we can do to measure all this stuff, very important to measure input parameters, is use some techniques like to measure doping density and distribution, which we don't do, phonon lifetime, which we don't do, and phonon coherence, which we don't do. So those things would be important variables to measure in the future. So the conclusion, there's a model that identifies key parameters. The role of phonons and coherence of phonons is clear in the model. It's a simple coupling mechanism, which may or may not be the actual mechanism, but if it's not, similar phonon mechanisms would have the same math, basically. You can use this model for leverage analysis, and I gave you some tools. Some from Einstein. There's a shorter version of this, but this is apparently what Einstein says. It can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible. That's what I tried to do. And then from Sherlock Holmes, when you've eliminated all that which is impossible, then whatever remains, however improbable, must be the truth, including those things from Alice in Wonderland. Okay, that's it.
Thank you, Dana.